Good day, this is Jim Pytel from Columbia Gorge Community College, Renewable and Energy Technology Program. This is EET 121, Digital 1. Today we're going to discuss some basic logic functions. And again, these are combinations of our three basic gates, not, and or. And depending on how you combine these gates here, you can come up with some pretty impressive and complex logic circuits. The most common logic circuits and logic functions that we're going to be dealing with is comparators, just one of them. We're just going to do a big list and we'll talk about each one. A comparator, basically all it is, it's comparing two numbers. Is it bigger, is it smaller, or is it equal? And that's the key thing. Is it equal? You can say yes or no, and if it's not equal, it's obviously bigger or smaller, okay? So there's going to be two numbers that are coming in, A and B, and there's going to be three outputs. If A is equal to B, if A is greater than B, or if B is greater than A. Only one of those can be high at any time. So if A is equal to B, that one would be high, the other ones would be low. If A was greater than B, what is the output of a comparator? If A was greater than B, this one would be high. If B was greater than A, that's it. That's all a comparator is. Okay, the next basic logic function is arithmetic operations. And the basic for all arithmetic operations is the adder. And believe it or not, you can make a subtractor from an adder. Trust me, I'll show you how to do it. A multiplier, which if you really think about it, a multiplier, all it is successive addition. Remember in fourth grade, you're like 4 times 4. Okay, 4 plus 4 plus 4 plus 4. You know, you can do it that way. But there's faster means to do it. Computers have all the time in the world. They just do repetitive, boring tasks over and over. That's exactly what computers excel at. And division, that's successive subtraction. And as I said earlier, you can actually make a subtractor out of an adder. Okay? So one quick note about our adders. So we're going to have an input for our number A that we want to add, our input B that we want to add, and there's going to be this output, our sum, and there's going to be another output here called our carry out. Okay? So what is a carry out? Well, think about this. You're adding two numbers together, and in our decimal system, just the traditional number that we have, just think 3 plus 9. You know, our sum in that particular case, our answer is 12. Our sum would be 2, and our carry out would be 1. It's basically representing the next column over. That's what a carry out is. And we'll go into these in a lot more detail later. There is a third input, though, called a carry in. And what the carry in for an adder is used for is so you can nest a bunch of adders together and create an adder for a large sequence of numbers. Okay, where the previous stages carry out is the next one carry in. Don't worry too much about that later. Now we'll talk about it much later, but just understand that the function of arithmetic can be performed with adders hooked up in special ways. Okay, the next basic logic function is code conversion. Actually, I'm just going to say code right now because code conversion is one of the functions. You know, just think about the languages that we speak. You can convert from English to Spanish, Spanish to English, English to German, any possible combination thereof. That's what a code converter does. It can convert from binary to BCD, binary to gray code to BCD, any combination thereof. conversion, just think of it as a translator. The next one for codes is an encoder. So an encoder recognizes the presence of an event and creates a code for it. Okay? Opposite, the decoder detects the presence of a code and indicates the presence of that code. Okay? We'll go into those. The next basic logic function is data selection. And this uses two basic circuits, a multiplexer and a demultiplexer. And these are often written shorthand, mux, demux. All these guys are switches. Okay, so a multiplexer, its symbol is this funnel-shaped thing, and that's exactly what it's doing. It's funneling multiple inputs to a single output. And a demultiplexer is the exact opposite. Well, actually, let's just draw it right here. It's taking a single input and spreading out to a number of outputs. So internally to a multiplexer is a switch. Same thing as a demultiplexer. So right now, computer A is talking to computer W. B, C, D, X, Y, Z. And now at a given time, the conversation switches. From B to X. And from C to Y, and so on and so forth, from D to Z. So what you're getting here is basically you are only using a single line. Serial communication, the advantage is a single serial line, lightweight, but you're routing a number of systems together. And this is how telephones work. There's not 200 lines going to every single person out there. It's one line, and you're allocated a certain amount of time that you speak. And no, you're not continuously connected to the person you're talking to, but you're enough that you can understand what's going on. And the key to how a multiplexer and a demultiplexer, again, that's the mux, that's the demux. The key to it is these are recipients, A, B, C, and D. Excuse me, these are the senders. These are the recipients. Everybody's got to have an address. So these are our address lines here. And you need to, okay, A wants to talk to X. A wants to talk to Z. You need to know who you're talking to there. Yes, you've added a couple lines here for those address lines, but it's still, you can route 64 systems onto a single line. That's the advantage for multiplexers and demultiplexers. All they are is taking individual data, putting onto a single line, sending it to the next guy. It's a little postman without the AK-47s. Okay, there's a couple different types of multiplexing. Time division multiplexing, TDM, you might have heard this before. You're allocated a brief block of time from second 1 to 2, A talks to X, whatever. And next second, the next guys get to talk. There's something else called frequency division multiplexing. This is very similar to your DSL lines over your phone line. It's the same line, but there's two frequencies on it. And that's why you have to put that little filter there. FDM, frequency division multiplexing. Let's stop talking about multiplexers and move on. The next logic function is storage. And this is where a lot of computers here come into play. They're storing our data. And no use in having data and just losing it. You got to hold it long enough to do something useful with it. So there's a couple different types of memory, or excuse me, storage devices. First one of them is a flip-flop, and a closely related device called a latch. And these are bistable, meaning they can take one of two states, either a 1 or a 0, and hold it indefinitely. Think of them as buckets of water. Either you're filled or not filled. And when you come back the next day, the ones you filled up should remain filled. The ones that are empty should remain empty. Okay? A register, that's a group of flip-flops and or latches stuck together. And normally they're stored in groups of 8 or multiples of 8. And 8 individual pieces of data. So individual pieces of data are called bits. 8 bits, that's a byte, B-Y-T-E, okay? So you've heard these terms already in computer speak. So there are two different types of registers, series and parallel. I'm just going to do 3 bits because 8 bits would be just terribly confusing. So to load a parallel register, let's say we want to store a number, binary number 101, which has the decimal equivalent of 5. We haven't gone over this yet, but we will. So say we want to store 101, decimal equivalent 5, into our 3-bit register. There's 2 ways of entering. We can enter serial, one after the other. So 101, then that moves over. Just think of this as a bus. You're loading a bus, one after another. Or you could simultaneously do this with a parallel register, and everybody gets on the bus at the same time. Okay? There are semiconductor memories, which is very similar to registers and flip-flops, and those are divided into ROM, read-only memory, and RAM, random access memory. So ROM, RAM. ROM, that's permanent. RAM, temporary. When you turn off the computer, it's gone. The last type of storage we'll deal with is magnetic and optical. These are mass storage and backup. And one of the final functions you're going to deal with is counters. And essential to counters, just think about 0, 1, 2, 3, where was I? Where am I at? You know, essential to counting operation, good counting operations, is remembering where you were. So if you've got a counter, chances are you've got some memory device in it too. Okay, so in your book, you've got a terribly confusing diagram of logic functions, some basic logic functions hooked up for a pill counting device in a factory setting. So it doesn't have to be that confusing if you take it one by one. So one could easily divide the system into human input and machine control. And the key to this whole thing is this comparator right here. What we want to do is set up a situation where each bottle is filled with a certain number of pills. And once it's filled to that number, we want it to advance to the next empty bottle and start it over again. And additionally, what we want to do is keep track of how many total tablets have been bottled. Okay? And just to be fancy, we're going to send our stuff to a remote location using a multiplexer. Okay, so the human input portion of it is this over here. What you're going to do is you've got a keypad and you're going to go ahead and press, I want 50 tablets into each bottle. And you get that 50 that you typed into the keyboard is going to be sent to an encoder where it encodes it into binary. And that is stored in registered A. And now that's sent to, whoop, that's not sent to there. That is sent the way they have it set up. Yeah, okay. They're going to go ahead and convert it again, and it's going to be sent to the comparator. And for your human understanding of this thing, it always helps to see what you just typed. So it's sent to a decoder, and that is sent to a display saying you just typed in 50 tablets. Okay, so again, like I said, the key to this whole thing is this comparator. So you said I want 50 inside each bottle. Well, this comparator is going to say the only input you're going to use, does A equal B? So B, assuming that A was what the human input right here was, B should probably be what the valve right here is reading. Okay, so how many tablets have gone through? So what we're going to do is we are going to, the sensor at the valve, we're going to read how many tablets go through using this counter device. So anytime a tablet goes through, a pulse is sent to the counter, and then it's going to be sent to the B. I'm sorry, guys. It's going to be sent to the B input of the comparator. When A equals B, when 50 tablets are in our inside our bottle here, we want something to happen, and that's that output right there. And the output that we want the valve to close, to shut that thing off, and we want this conveyor belt to advance, putting another empty bottle in the place. And when that empty bottle is in place, we need to reset our counter back to 0. Okay, so I know it looks kind of confusing at the beginning, but that's the basic operations here. The human input side where you say 50, and the machine control where you're making sure 50 is there, and once it's reached 50, it's turning off the valve, advancing to the next empty bottle, and resetting the counter. So now, since you are in business here, you want to keep track of what's going on. Okay, so that's what we're going to do, is we're going to start adding up. That's our new input there. So we just bottled 50. And what we're going to do is we're going to add that with our previously stored sum. Okay, and our previously stored sum is stored here in this register B. Okay, so how do you add, how do you increase something if you've got a certain value previously and you've just added more to it? All you're going to do is take that value previously and add it to the new incoming data. And then what you can do is restore it. Okay, so now what we can do is we are going to go ahead and, again, we want to know where we're at, how many total have we bottled. Do our code converter, because maybe we're using a different code on this side that the decoder doesn't recognize. decode it. And what a decoder is going to do, let's say you have currently bottled 550 tablets. And again, since you're in business, you want to send this to your remote office. Let's say there's a bunch of different systems that are being sent into here, and you can use this multiplexer. Send this to your remote office over a single line. And again, there's a number of different systems out there. For this particular system, it's being sent to register C, decoder C, and it's displaying on the big boss man's wall that you just go at, that your factory has bottled 550, or this particular machine has bottled 550 tablets. Yeah, I know there's a lot of lines there, but there's only a couple functions, and used in a pretty logical operation, you've developed a means of human interface and machine control.